So welcome back for part 2 of fossils. We're going to take a look at how fossils fit into stratigraphy. And just to reiterate about the geologic range, I showed you an adiosaur earlier, and now we're looking at mammoths. This is actually a life-size replica. And right here you see a woolly rhinoceros skeleton and then a model of a replica of a woolly rhinoceros. Well, we can isolate their time frame or their geologic range to the last ice age. So that's really important in stratigraphy because fossil succession is dependable. The theme of geology, especially in historical, is that life went from very simplistic to more complex. That doesn't mean we lost simple life, because the original life forms on Earth that made stromatolites, they're still with us today. But we continually get diversification, evolution, changing organisms in the planet and around the globe. And that will continue as long as we have the circumstances that will allow life to flourish. What I mean by that is as long as we have environmental conditions that can sustain life. So when we talk about stratigraphy, we need to define what a formation is, a geologic formation. In physical, we touched on this, but it's super important in historical because there's so many geologic formations that we'll discuss this semester by name that have character and history that are important to our studies. The first geologic formation was described in Germany in 1770. And what is a formation, really? It is a distinctive series of rock layers, meaning strata. So the root word of stratigraphy is strata, meaning rock layer. And these rock layers have originated through the same time period, the same geologic formation processes, and share similar characteristics in morphology, mineral content, rock content, and even fossils. So a formation is the most basic level of description when we're getting into a description of rock layers that have been mapped around the globe. What are some of the challenges for assigning formations? And I'm using Sedona here as an example. When formations are described, we have to describe them from their basal contact with the prior or the one formation beneath them and their uppermost extent of their formation. So describing the upper and lower boundaries can be challenging if you've got lenses, and I don't mean lenses from the point of view, I mean actual lenses or layers of intermittent rock that doesn't make the same character or share the same character as the rest of the rock. So that makes the contact between one layer to the next layer above and below it fairly challenging to identify, which is one of the most challenging parts of mapping out stratigraphy in the field. Formations usually include more than one layer, and which are members, by the way. So you can have a formation be like a family name, and to think about your family name and then the individual people in your family. Well, the individual members of a rock formation would be like your family members. So formations are then put together in groups that share similar history, character, and so forth. So the bigger sections are called groups, and then you get formations, and then the most specific one would be a member. Even groups can be put into series. There's a level above that. But we'll be looking at a few groups this semester, and certainly formations by names and individual members. So this whole section right here is one big member, this red slick rock right in here. Different formation name right here. Within each of these are specific members that make up what we call the Bell Rock Formation. And actually it's the Schnebly. It's what we call the Schnebly Hill Formation. But in the Schnebly Hill are a number of members that make up this. For example, the Bell Rock member. For example, the Fort Apache member. So there's individual members, and the newest geologic formation that's showing at the top of this rock, or the youngest actually, is the Coconino Sandstone, which happens to be a famous rock layer in the Grand Canyon. Each one of these formations and specific members tell us a story about the conditions that were present in geologic past. So when we look at a formation, you have to look at the composition of the material that makes it up. So you're looking at the mineral grains in the rock layer, the character or color of the rock layer, textural properties. What I mean by that, does it have ripple marks? Does it have cross bedding? Does it have mud cracks? Does it have soil marks? Things of that nature that you learned about in physical. The thickness and the morphology, meaning the shape of the actual formation. Sometimes formations have been bent out of their original flat layer to make synclines, anticlines, monoclines. Are there fossils? And if so, what are the character, the types? What kind of environment would they live in? And then anything about the outcrop itself that could give you characteristics. So a term that's associated with stratigraphy is called lithology. Lithology is the total sum of the above characteristics of a formation, and its prefix lithos actually refers to the term rock. So we look at the lithology of a rock, and I would say that's its personality in short. That's important because lithologies, even for the same geologic formation, can change from area to area, giving you clues that the depositional environment slightly was altered over time. Formations were being named in Europe back when we first started making formation names, and they were thought to have been destined to become the standard naming system. Well, geologists found fossils and rocks that were similar all over Europe, and then they assumed that the evidence to support these layers were universal. Well, that's another challenge because not all formations are universal, meaning they're not global. There's some that actually can be found globally, but many are regional. And to us, regional seems like a small geographic area of a city or a cluster of cities. We're talking about regional in the sense of hundreds of miles here. Geologists realized that the similarity of fossils and similar types of sedimentary rocks could be an indicator, a clue, as to how they were formed. So I look at this rock right here. This is actually an angular unconformity in Cody, Wyoming. So we were traveling there on my sabbatical, and I saw this. I was like, wow, look at that angular unconformity. You just don't see that every day. And you can see the unconformable contact right here, and then the rock changes right here. So if I zoomed in, this is a conglomerate rock. This is a sandstone. That tells me that something changed between those time periods. We're probably missing a chunk of rock where that rock, well, we are, don't just think, I know. We're missing a chunk of rock right here. Something's missing that probably used to be there. So we got to cover depositional environments. So transitional areas would be like your beach lines, your marine deltas, your tidal flats, the sand dunes that are along the beach, and then also barrier islands. So marine is your continental shelf, your inner and outer. So the inner is going to be like what you see right in here. Your continental slope, which is going to be where your continental shelf makes an abrupt dip, and then a continental rise, which receives all the deposits from turbidity currents. And then your carbonate shelves, which are very important and historical, which you'll see when we get to marine transgressions and regressions and slough sequences. Deep marine and evaporite deposits. So all of these play a role in what you'll see the rest of the semester. So let's start with terrestrial environments. This would be a classic terrestrial environment in Glacier National Park. This would be a fluvial environment. Rivers are fluvial. So if you're new to these terms, you need to make sure you know them because we'll be discussing them throughout this semester. There are two basic groups of types of river systems that you'll likely see, and they're important because we find evidence of both in the rock record. Braided streams is not what you're seeing right here. Braided streams is where, like a person's braid in their hair, it would represent intertangled river systems where you have more than one tributary, and that comes usually from wide river basins that are having a constant source of water. For example, and most commonly, melting glaciers. So at the toes of glacier, the terminus of a glacier, you should expect to see ice melting and it producing wide scale river systems that tend to have wide river basins, and they make these shallower waters that flow intermittently through each other and create a very distinctive look. You will not see mud rock very often, meaning shales, in this environment. Instead, what you'll see is conglomerates and sandstones, lots of moraine type deposits that you might find there. So it's very gravelly. Unlike a meandering stream, which is typically what you see right here, meandering streams deposit mud rocks, sometimes sandstones, even conglomerates during flood conditions. So this is the standard type of stuff that is in most streams that aren't from melting glaciers. And meandering streams leave behind very specific patterns of rock type material in their riverbeds. So let's look at Eolian environments. These are going to include alluvial fans, which are poorly sorted deposits from debris flows or from tops of mesas or buttes or mountains where materials by gravity work their way down, sometimes even by flowing water. So you can find sandstones, conglomerates, breccias, this type of rock, but they're very poorly sorted because they just drop from a high location and just go splat at the bottom and kind of spread out. There's some alluvial fans happening right here in Death Valley National Park, so very common to see that, especially in the desert. Sand dunes are very common in desert environments. Now you can make sand dunes, coastal sand dunes as well, barrier island sand dunes, but sand dunes in the desert should show a high angle of cross-bedding. So what does that look like? It typically somewhere between 32 and 34 degrees. And the reason being is the angle of repose for dry sand is about that degree marker. So you can always tell if you're dealing with desert sand simply because of two things. One, you have the angle of a high angle of crossbedding, and second of all, you have frosted quartz grains. And here's what I mean by that. In a beach environment, water acts as a lubricant. So it kind of puts a cushion between the individual grains of quartz, and so they don't bang together and get frosted like if you took marbles, clear marbles, and smashed them together, they kind of get frosted. So you can imagine in sand dunes that are in the desert, Eolian environments, they don't have that cushion, so they tend to be frosted. So those are the several characteristic signature patterns of Eolian environments versus river or beach deposits, meaning cross-bedding, that you might find in sand dunes along those environments. Playa lakes. These are little areas that are depressions in flat land that will accumulate water, especially after a rain event. They're basically made up of mudstones, siltstones, and very commonly have evaporite deposits. So we find these very typically in Eolian rock formations that showed evidence of fluxes of flash flooding. Well, we would call that monsoon season out in the western states right now. So those same states that are in the western states that are still arid today, considered desert-like, they also demonstrate the same type of phenomena. So another terrestrial environment is glacial. There are several different types of deposits that are very important to our studies and historical, starting in the Paleozoic all the way through the last ice age. So there's a difference between outwash deposits and moraine deposits. Outwash deposits are made up of conglomerates and have characteristics of braided streams, much like these right here. This is Mount Rainier, and there's some melting glaciers there. Do you see all this rubble deposits there? That is very characteristic of outwash deposits from a melting glacier stream. Moraine deposits are very unsorted by size. They represent sands and gravels from melting glaciers that dump it at the terminus of where that glacier is. So they have a different appearance and usually much thicker than outwash deposits that you'll find in the rock record. So in glacial environments, we look for a couple of clues that tell us they were there. Varb deposits are areas where you'll find silt and clay, like silt and shale, that gets deposited from melting glaciers, icebergs in particular, or the terminus of a glacier that has some silt from crunching up bedrock and making glacial flour. And that melts and that sediment feeds to the bottom of the lake. So you can actually determine cycles of warming and cool trends by looking at barbs in glacial lakes. Drop stones are stones that get carried by icebergs that were in the actual glacier. So when the glacier calves, in other words, it breaks off and makes an iceberg, that rock's still in the iceberg until it melts, and then it drops to the bottom of a lake, which should definitely not have giant rocks in the bottom of the lake. It's just like somebody dropped them there. This is a glacial erratic right here, and erratics are stones that are plucked off of their source rock and carried with the glacier until the glacier melts. Sometimes that could just be tens of kilometers, sometimes that's hundreds, if not 1,000 plus kilometers from home. So glacial erratics were proven by a guy that we'll learn about later in this semester when he studied glacial erratics in Canada. So another type of environment to look at are transitional, and keep in mind that's the boundary marker between where the coast is, real terrestrial land, out to where the continental shelf starts. So these are areas that should have characteristics of both ocean and terrestrial environments. So marine delta is this type of situation right here where the water flows into an adjacent water body. In this case, this is the Pacific Ocean. This is right where Olympic National Forest or Park is in Washington State. And I was following the stream, and it came and fed into the Pacific there, and you can see where a bunch of sediments falling out. Well, that's a marine delta. They're going to be made up of shales and mud rocks and sometimes some sands and silts. You should find both marine and terrestrial fossils because you'll get high and low tide influences to this area. Beach deposits, like you see here at the Green Sand Beach in Hawaii at South Point, are composed of fragments from several different places. The bedrock of the continent, the terrestrial, that's been broken up by erosion, usually by wave action, which is certainly the cause of this green sand right here. The green sand comes from basalt that has that olivine in it and weathers out when this water hits it. So this is a green beach, and it really is green. I've been there multiple times, can tell you it is. Another source of stuff that you'll get in beach over time as it ages, you'll usually get some carbonate life, meaning algal reefs and coral reefs that start to develop. In this particular case of Hawaii, that's not the case because Hawaii is so geologically young. It's virtually got only algal reefs. You got to go to places like Maui and Kauai where the islands are older to have developed actual coral reefs to see. So good to know if you're going to take a trip to dive in Hawaii. So beach deposits will have rounded sandstones. They're very, what we call kind of mature sandstones because the beach surf constantly is shaping and creating a similar size grains. And remember, they shouldn't be frosted like you would see in an Eolian beach or what we call a sand dune deposit. You might see small scale crossbedding here, but you're not going to see the same stuff like you would in an Eolian environment at a degree angle of 32 to 34 degrees. So whenever you see high angle crossbeds, that's a clue that you've got desert, not beach deposits. Barrier islands include beach sands, sand dunes, tidal flats, and even coral reef material. Beaches, just like we saw with Hawaii, will have lots of shelly fragments, lots of terrestrial material, and then the sand dunes may look like Eolian sand dunes, but they'll have shelly fragments with them. Tidal flats are made up of mudstones like you see right here and typically have ripple marks. So I'm in Glacier National Park where I'm stepping on this ripple mark right here, and that kind of gives us a clue right there that we had water come in, water coming out, oscillating over time, and that is important to recognize with a changing depositional environment. So when you see ripple marks, especially in context with other clues, you can tell if you're in a tidal flat in a transitional environment. So for true marine environments, that would be the stuff outside of the coastline from transitional. This is marine, this is marine. The continental shelf deposits are going to be directly correlated based on size to the depth of the water and distance from terrigenous material. If you remember from physical, terrigenous means land-derived. So the further you are away from a coastline, the less terrigenous material you should see in the water, simply because grains can't get carried immense distances from shore. So the inner shelf deposits includes cross-bedded sandstones that have formed formed ripple marks and marine fossils. These would be things closer to shorelines. And the outer shelf would be stuff like this out here that's made of mud rocks and some sandstones and marine fossils. But their continental shelf deposits are as variable as the depth and the source of material that makes them up. So another place in the marine environment is to look a little deeper, where the continental slope marries up with the continental rise. So this is your continental slope right here. That's where the continental shelf, this is your continental shelf right here, makes an abrupt dip change or grade change. And then it deposits a bunch of sediment from turbidity currents down here on the continental rise. These types of deposits are called turbidites, and what they are these materials that carry down the continental slopes and into the continental rise. The carbonate shelf is one we'll be discussing a lot this semester, because with the 6 slough sequences that you'll be learning about, lots of carbonate rock got embedded on the continent where it shouldn't be today, where it's exposed land. These are deposits made up of limestone and dolostone. The limestone often has lots of marine fossils and evidence of turbidity currents, which are fast-moving currents underwater. Sometimes they even look like tornadoes, and they can make ripple marks on the sand. I've seen them in places like Australia, Jamaica, Bahamas. I've even witnessed a turbidity current in the Bahamas, underwater, I might add. So there's still one more environment to discuss, and that's the deep ocean. These deposits are made of pelagic clay, calcareous oozes, and siliceous oozes. You might be, oh my gosh, what are those words? Pelagic clays are going to be your deep water clays. So they're the remaining detrital material that takes a long time to settle out at the bottom of the deep ocean. Calcareous oozes are going to be your stuff that's made out of calcium carbonate, basically material like dead animals that sinks to the bottom of the ocean. And then your siliceous oozes are those that are made out of silica-based animals. So siliceous oozes are going to be have harder fragments of material than you would find in your calcareous. This kind of shows you in the oceans where we have it. So here's North America. You can see calcareous oozes are this color right here in this sections. And then siliceous oozes are very distinguished where they are found around the globe. So there's not as many of them as there are calcareous oozes. Your deepest water materials are pretty much going to be found in your areas that form in the deep water ocean, your pelagic clays. Another environment to consider is when the ocean evaporates. This is primarily going to happen on continents when sea level rises and falls, and those are called evaporite deposits. These occur, like you see right here at the Mars Desert Research Station. Here's a really big gypsum layer. There's more gypsum down here, showing us periods of wet, made playa lakes or something like it, evaporated and left behind its solids. It gets another layer of regular deposition. Then we get another layer of showing that we had a wet environment and it dried up. So evaporite deposits are not only useful clues, they're also beneficial to us for economic gain. So when we think about depositional environments, one of the best places to look to show this is Zion National Park, my personal favorite national park. And you look at this, can you see the cross-bedding? This is here, and you see where the beds just abruptly stop right here. By the way, that's called a truncated edge. So what happened was these hit the angle of repose for dry sand, which is around 32-ish degrees. And then we get some kind of high wind or storm that came in and blew off the top and just kind of took the frosting off. And when it did, a new set of sands built on top of it. So the Zion National Park, all of this stuff is the same geologic formation known as the Navajo Sandstone. You'll learn about that when we get to Mesozoic era, specifically Jurassic. And the early Jurassic was known as the greatest Eolian event of all time. So more to come on that, but as you look at this rock, it should tell a story. Some clues are there. More clues beyond just the cross-bedding would tell us that it's Eolian. And hopefully you remember what that clue is. We need a little microscope to do it, but what would you look for to determine that those are really cross-beds from a desert as opposed to a beach line? So when you interpret depositional environments, you need to look at the clues. So this is the Waco wetlands, and you can see all this green material, very slow moving, low energy environment. So if this plant material dies, it's going to make organic rich layers like coal. So that is important to understand and interpret even modern day environments, what they could turn into in geologic future should those rock layers be preserved. So let's take a break and we'll see you back for the third part of fossils. More to come. See you in a little bit. Bye.